Hello and welcome. Tonight you can relax and listen quietly as we explore calm, mysterious facts about black holes. Black holes are among the most misunderstood objects in the universe. They are often described as violent or destructive, yet most of the time they are quiet, stable, and distant. A black hole does not actively pull things toward it. It does not hunt or chase. It simply exists, influencing its surroundings in the same calm way any object with mass does. At their core, black holes are regions of space where matter has become extremely concentrated. This concentration bends space and time so strongly that light itself cannot escape from a certain boundary. That boundary is known as the event horizon. Beyond it, information cannot travel outward. From the outside, this horizon appears smooth and silent, with no visible activity. Despite their reputation, black holes are not holes in space. They are not empty. They are objects with mass, density, and structure, formed through natural processes that follow the same physical laws as everything else in the universe. They are not breaks in reality. They are part of it. Most black holes form when very large stars reach the end of their lives. These stars spend millions of years balancing two opposing forces. Gravity pulls inward, trying to collapse the star. Energy produced in the star's core pushes outward, preventing collapse. For most of a star's life, these forces remain in balance. Eventually, the star runs out of fuel. When this happens, the outward pressure weakens. Gravity begins to dominate. The star collapses inward under its own weight. For some stars, this collapse stops, forming dense objects like white dwarfs or neutron stars. For the most massive stars, the collapse continues further. When the core collapses beyond a certain limit, no known force can stop it. Space itself bends inward. Matter is compressed into an extremely small region. A black hole is born. From the outside, this process may be accompanied by a supernova, a brief and distant burst of light. After that, calm returns. Once formed, a black hole can remain unchanged for billions of years. It does not need fuel to survive. It does not burn or emit light. It simply exists, influencing nearby space through gravity. If nothing comes close, nothing happens. Many black holes spend their entire existence in silence. There are different kinds of black holes, varying greatly in size. Some are only a few times more massive than the Sun. Others are millions or billions of times more massive. These larger ones are found at the centers of galaxies, including the Milky Way. They are known as supermassive black holes. The supermassive black hole at the center of our galaxy is called Sagittarius A star. It is about 4 million times the mass of the Sun. Despite this enormous mass, it is relatively quiet. It does not actively consume stars. Most of the time, it is surrounded by empty space. Black holes do not grow endlessly. They grow only when matter falls into them. This can happen when gas drifts too close or when a star passes near enough to be disrupted. These events are rare, space is vast, and distances between objects are large. Most black holes go long periods without absorbing anything. When matter does fall toward a black hole, it does not disappear instantly. It often forms a disk around the black hole, called an accretion disk. In this disk, matter heats up as it spirals inward. This heating can produce light and radiation, making the region around the black hole visible from far away. This light does not come from the black hole itself. It comes from the matter outside the event horizon. The black hole remains dark. Only its surroundings glow, briefly revealing its presence. Time behaves differently near a black hole. As matter approaches the event horizon, time slows down relative to distant observers. To someone far away, objects falling toward a black hole appear to slow and fade, never quite crossing the horizon. To the falling object, time continues normally. This difference does not create drama. It simply reflects how gravity affects time. Inside the event horizon, our current understanding becomes limited. Physics, as we know it, can no longer fully describe what happens. This does not mean chaos. It means we lack complete information. The black hole remains calm and stable from the outside, even if its interior is mysterious. Black holes do not erase the universe around them. They do not consume everything. In fact, if the sun were replaced by a black hole of the same mass, Earth would continue orbiting in the same way. Gravity would remain unchanged. Only the light and warmth would be gone. This shows that black holes are not uniquely dangerous. They obey the same gravitational rules as other objects. Their difference lies in how compact they are, not in how they behave at a distance. Over extremely long periods, black holes may slowly lose energy through a process known as Hawking radiation. This process is incredibly weak. For stellar mass black holes, it would take far longer than the current age of the universe for any noticeable change to occur. For now, black holes are effectively permanent. They drift through space, often unnoticed. Many exist far from stars or planets. Some move through galaxies quietly, carrying their mass with them. They do not announce themselves. They do not need to. Black holes remind us that the universe contains extremes that are stable rather than violent. They show how gravity, space, and time interact in subtle ways. They are not monsters or anomalies. They are natural outcomes of cosmic evolution. As you listen, there is no need to imagine falling or approaching anything. These are distant objects, far beyond everyday experience. They exist calmly, governed by rules that do not change suddenly. The universe does not rush near black holes. Motion remains smooth. Time continues. Space bends gently. Everything proceeds without urgency. And as the night continues, these distant objects remain where they are, silent and steady, while the narration moves on slowly, allowing rest to deepen without effort. Black holes are invisible by nature. They do not emit light, reflect light, or glow on their own. Because of this, everything we know about them comes from how they affect their surroundings. Astronomers do not see black holes directly. Instead, they observe the motion of stars, gas, and light nearby, and infer the presence of something massive and compact. One of the first clues that black holes existed came from stars behaving in unexpected ways. In some regions of space, stars were orbiting around empty-looking points, moving very fast in tight paths. The only explanation was that a large amount of mass was present, even though nothing visible could be seen. This invisible mass matched predictions made by theories of gravity. Gravity near a black hole behaves smoothly but strongly. Far away, its pull is no different from that of any other object with the same mass. Close to it, space becomes increasingly curved. Paths that would normally be straight begin to bend. Light itself follows these curves, changing direction as it passes by. This bending of light is known as gravitational lensing. It allows astronomers to detect massive objects, even when they emit no light. When a black hole passes in front of distant stars, it can briefly magnify or distort their appearance. These subtle effects reveal the black hole's presence without any dramatic signals. Most black holes are small compared to the space around them. Even a black hole with the mass of several suns would have an event horizon only a few tens of kilometers wide. In the scale of space, this is extremely small. Because of this, black holes are easy to miss and difficult to detect unless something comes very close. Despite popular images, black holes do not pull in matter from great distances. Objects must pass quite close to be affected in a noticeable way. Stars can orbit black holes safely at large distances, just as planets orbit stars. Stability is far more common than disruption. When matter does approach closely, it often forms an accretion disk before crossing the event horizon. This disk is flat and rotating, shaped by angular momentum. Friction and compression within the disk cause the material to heat up gradually. This heat produces radiation that can be observed across vast distances. Some of the brightest objects in the universe are powered by black holes, not because the black holes shine, but because the surrounding matter does. Quasars and active galactic nuclei are examples of this. They appear bright because enormous amounts of gas are slowly spiraling inward, releasing energy before disappearing from view. Even in these cases, the process is controlled and continuous rather than explosive. Matter moves inward along predictable paths. Energy is released steadily. The system can remain active for millions of years before quieting again. Not all black holes are active. In fact, most are inactive. They sit alone, surrounded by empty space, with no nearby matter to absorb. These black holes are completely dark and silent, detectable only through their gravitational influence. The idea that black holes destroy everything nearby comes from misunderstanding scale. Space is mostly empty. The chance of a black hole encountering a star or planet is very low. Even within galaxies, distances between stars are immense. Most black holes will never interact closely with anything for their entire existence. Inside the event horizon, our understanding becomes uncertain. According to current theories, matter continues collapsing inward toward a region called the singularity. This is a point where density becomes extremely high. However, this description comes from equations pushed beyond the limits where they can be tested. The singularity is not something that can be observed. It is hidden behind the event horizon. From the outside, the black hole behaves in a simple and predictable way, defined by mass, spin, and electric charge. This simplicity is sometimes described as the no-hair property of black holes. Spin is an important characteristic. Many black holes rotate, sometimes extremely fast. This rotation twists the space around them, an effect known as frame dragging. Nearby matter and even light are gently pulled into this rotation, following curved paths. Rotating black holes create regions where space itself moves. In these regions, objects cannot remain still relative to distant space. Everything is carried along smoothly. This does not feel violent or chaotic. It is a continuous effect of rotation on space-time. Despite these extreme properties, black holes are remarkably stable. Once formed, they do not change quickly. Their mass increases only when matter falls in. Their rotation slows only very gradually. Over cosmic timescales, they are among the most persistent objects in existence. Black holes also play a role in shaping galaxies. Supermassive black holes at galactic centers influence the motion of stars nearby. They can also regulate how much gas remains in a galaxy, indirectly affecting star formation. This influence is subtle and long-term rather than immediate. Galaxies and black holes appear to evolve together. The mass of a supermassive black hole is often related to the size of the galaxy around it. This suggests a deep connection formed over billions of years, guided by gravity and time. Even so, black holes do not control galaxies in a direct sense. They do not command or dominate. They are part of a larger balance, contributing to structure rather than disrupting it. From a distance, a black hole does not appear special. Space around it remains quiet. Stars continue their paths. Light travels normally. Only when examined carefully do its effects become apparent. This quiet nature is what makes black holes suitable for calm exploration. They represent extremes of physics without constant activity. They are reminders that the universe can contain profound mysteries without noise or urgency. As you listen, these distant objects remain far away, unchanged by attention. They continue their slow existence, shaping space gently, while the narration moves forward at an even pace, allowing rest to continue naturally. Black holes also help us understand the limits of physics. They sit at the boundary between what we can measure and what remains unknown. The laws that describe gravity work extremely well in most situations, but near a black hole, especially close to the event horizon, those laws are stretched to their limits. This does not cause instability. It simply reveals how much remains to be explored. One of the most interesting aspects of black holes is how they affect time. According to modern physics, gravity influences not only motion, but also the passage of time itself. Near a black hole, time passes more slowly compared to faraway regions of space. This slowing is gradual and predictable, increasing as one approaches the event horizon. From a distant viewpoint, an object falling toward a black hole appears to slow down. Its signals take longer to reach the observer. Its light becomes dimmer and redder. Eventually, it fades from view. There is no sudden disappearance. The process is smooth and continuous. For the object itself, nothing unusual happens at the horizon. It does not experience a sudden force or a dramatic event. Time continues to flow normally from its perspective. This difference in experience highlights how time is relative, shaped by gravity and motion rather than absolute. Black holes also influence how information behaves. According to current understanding, information about objects that fall into a black hole is not destroyed. Instead, it becomes encoded in subtle ways at the event horizon. This idea is still being studied and debated, but it suggests that black holes preserve order rather than erase it. This question of information has led to deep insights about the nature of space and reality. It connects black holes to quantum physics, the study of the smallest scales in nature. These connections are complex, but they point toward a universe that is more unified than it appears. Despite these deep questions, black holes remain externally simple. From the outside, all black holes of the same mass and spin behave identically. They do not carry visible traces of what formed them. A black hole created from a massive star behaves the same as one formed through mergers, as long as their properties match. Black hole mergers are another important phenomenon. When two black holes orbit each other, they gradually lose energy through gravitational waves. These waves are gentle ripples in space-time that spread outward at the speed of light. They are extremely weak by the time they reach Earth, yet sensitive instruments can detect them. The detection of gravitational waves confirmed predictions made decades earlier. These signals arrive as faint vibrations, lasting only fractions of a second. They carry information about events that happened billions of years ago, far beyond our galaxy. Even these powerful events reach us quietly. After a merger, the resulting black hole settles into a stable state. Any irregular motion fades away. The system becomes calm once again. This settling process happens quickly, restoring simplicity after change. Gravitational waves do not disturb space in a lasting way. They pass through, leaving everything as it was. Planets, stars, and people are unaffected. The universe absorbs these ripples without consequence. Black holes can also slowly move through space. Some are ejected from their original locations due to gravitational interactions. These wandering black holes drift through galaxies or intergalactic space. They carry no visible sign of their presence, moving silently through darkness. If a black hole were to pass near a star system, its effects would depend entirely on distance. At large distances, nothing would change. Only at close approaches would orbits be altered. Such encounters are extremely rare. The rarity of close encounters emphasizes how empty space truly is. Even in crowded regions like galactic centers, distances between objects remain vast. Stability dominates over interaction. Black holes do not grow rapidly. Even those at galactic centers grow slowly, accumulating mass over billions of years. Their growth reflects patience rather than urgency. Time is their primary resource. Some black holes emit narrow jets of particles along their rotational axes. These jets can extend for great distances. They are produced by interactions between magnetic fields and rotating matter outside the event horizon. Even these jets are stable and well-structured, maintaining their form across space. Jets do not come from the black hole itself, but from the environment around it. They are another reminder that black holes influence without acting directly. The black hole remains dark. Its surroundings respond. Over cosmic time, black holes may be among the last remaining objects. As stars fade and galaxies drift apart, black holes persist. Their slow evaporation through Hawking radiation takes unimaginably long periods. For now, they are effectively eternal. This persistence gives black holes a quiet presence in the universe. They are not events, but states. They do not rush. They do not change quickly. They simply remain. As you listen, these distant objects continue their steady existence. They rotate, drift, and shape space gently, far removed from daily life. There is nothing to anticipate and nothing to resolve. The universe continues at its own pace, and the narration follows calmly, allowing rest to deepen as the night goes on. Black holes also reveal how space itself can behave like something flexible rather than rigid. Near a black hole, space is not simply a backdrop where events happen. It becomes active, curved, and responsive. Paths that would normally be straight begin to bend. Distances stretch in ways that are not immediately intuitive. This curvature is not violent. It is smooth and continuous. This bending of space explains why black holes can influence light. Light always follows the straightest possible path through space, but when space is curved, those paths curve as well. As a result, light passing near a black hole can be deflected, redirected, or gently wrapped around it. This creates effects such as rings and arcs of light, faint and subtle, visible only with careful observation. In some cases, light can orbit a black hole briefly before escaping. These paths form what is known as the photon sphere. Here, light moves in closed loops, held in balance between gravity and motion. These orbits are unstable, meaning light does not remain there long, but their existence highlights how gravity can influence even massless particles. Despite these extreme effects, the region around a black hole is not chaotic. Motion remains predictable. Equations describing gravity still apply. The environment is calm unless disturbed by incoming matter. Most of the time, nothing passes close enough to experience dramatic changes. The idea that black holes tear objects apart comes from specific scenarios. If a star approaches too closely, tidal forces can stretch it, pulling different parts at different rates. This process, called spaghettification, sounds dramatic, but it occurs gradually. The star is stretched over time, not instantly destroyed. For supermassive black holes, these tidal forces near the event horizon are actually weaker than those near smaller black holes. This means that, in theory, an object could cross the event horizon of a very large black hole without experiencing extreme forces immediately. The transition would be smooth from the outside perspective. This contrast shows that size matters when it comes to black holes. Smaller black holes have stronger tidal effects near their horizons, while larger ones are gentler at that boundary. Both follow the same physical rules, applied at different scales. Black holes also interact with magnetic fields. When charged particles move near a rotating black hole, they can generate strong magnetic structures. These fields influence how matter flows, shaping accretion disks and guiding jets. Again, these processes are orderly rather than explosive. Accretion disks themselves are layered and structured. Matter closer to the black hole moves faster, while matter farther out moves more slowly. This creates friction and heat, but the system remains stable. Energy is released gradually, allowing the disk to persist for long periods. Not all accretion disks are bright. Some contain very little material and emit minimal radiation. These disks are nearly invisible, contributing to the quiet nature of most black holes. Activity depends entirely on environment, not on the black hole itself. Black holes do not prefer chaos. They respond only to what is nearby. If space around them is empty, they remain inactive. This makes them passive participants in the universe, rather than active agents. The study of black holes has also improved our understanding of time itself. Near strong gravity, clocks run at different rates. This effect has been measured near Earth and around stars. Black holes simply extend this effect to its extreme. These differences in time do not create paradoxes in daily life. They remain consistent and predictable. The universe adjusts smoothly, maintaining internal coherence. Black holes also help test ideas about the beginning and end of the universe. The same equations that describe black hole interiors also describe the early universe in some models. This connection suggests that understanding black holes may also help us understand cosmic origins. Yet despite these deep connections, black holes remain local objects. They do not influence the expansion of the universe. They do not alter cosmic destiny. They exist within the larger structure, shaped by it and contributing quietly. When black holes merge, the resulting object quickly settles into a simple form. Any irregular motion fades. The system radiates away excess energy through gravitational waves, leaving behind a stable, rotating black hole. Calm is restored almost immediately. This tendency towards stability is common throughout the universe. Disturbances are temporary. Equilibrium is long-lasting. Black holes exemplify this pattern clearly. They also remind us that mystery does not require activity. Something can be deeply unknown while remaining still. Black holes contain regions we cannot observe, yet their presence is steady and predictable. As the night continues, these distant objects remain far beyond reach, unchanged by time or attention. They continue shaping space gently, without sound or urgency. The narration follows this same rhythm, moving slowly and evenly, allowing rest to deepen as thoughts drift quietly onward. Black holes also help explain how energy moves through the universe. While they do not emit light themselves, they influence how energy is released around them. Matter falling toward a black hole loses energy as it spirals inward, converting motion into heat and radiation. This process is one of the most efficient ways energy can be released in nature, yet it happens smoothly rather than explosively. As matter circles closer and closer, its motion becomes more ordered, paths tighten. Speed increases gradually. The system does not collapse all at once. It evolves step by step, guided by gravity and conservation laws that remain consistent everywhere in the universe. This gradual process allows astronomers to study black holes indirectly. By observing the radiation emitted by nearby matter, they can estimate a black hole's mass, rotation, and environment. These measurements are careful and slow, relying on long-term observation rather than sudden discovery. Black holes also influence how galaxies age. In some galaxies, periods of black hole activity release energy into surrounding gas. This energy can gently heat the gas, preventing it from collapsing into new stars too quickly. In this way, black holes may help regulate the pace of star formation, keeping galaxies stable over long periods. This influence is not constant. It occurs in phases, separated by long, quiet intervals. Most of the time, the black hole remains inactive, and the galaxy evolves slowly. Activity and calm alternate, creating balance rather than disruption. The relationship between galaxies and their central black holes appears to be deeply connected. Larger galaxies tend to host larger black holes. This connection suggests that both grew together over billions of years, shaped by shared history rather than direct control. Despite this connection, black holes remain small compared to their galaxies. Even the largest supermassive black hole occupies a tiny fraction of its galaxy's volume. Space around it remains mostly empty, allowing stars to move freely. Black holes are also important for testing theories of gravity. Extreme conditions near them allow scientists to compare predictions with observation. So far, the behavior of black holes matches expectations remarkably well, reinforcing confidence in our understanding of gravity on large scales. At the same time, unanswered questions remain. The exact nature of the singularity, the fate of information, and the unification of gravity with quantum physics are still open topics. These questions do not create instability. They simply reflect the limits of current knowledge. Black holes remind us that mystery can exist without danger. Something can be unknown without being threatening. The universe contains regions we cannot see, yet it remains coherent and calm. From far away, black holes blend into the background of space. They do not glow or flicker. They leave no visible mark unless matter passes nearby. Most of the universe remains unchanged by their presence. This quiet existence allows black holes to persist for immense spans of time. They are not temporary events, but long-lasting states. While stars burn out and galaxies evolve, black holes remain, carrying their mass forward into the distant future. Over time, scales far beyond human experience, black holes may slowly lose energy through subtle processes. This change is so slow that it has no effect on the present universe. For now, black holes can be considered permanent features of cosmic structure. As you listen, these distant objects remain where they are, silent and steady. They do not move closer. They do not demand attention. They simply exist, shaped by gravity and time. The universe does not hurry around black holes. Motion remains smooth. Energy flows predictably. Space curves gently. Everything continues without urgency. And as the narration continues, the pace remains slow and even, mirroring the steady nature of these distant objects, allowing rest to deepen naturally as the night goes on. Black holes also reveal how motion behaves in extreme conditions. Near one, the usual sense of direction becomes less clear. Paths curve inward, and movement that would normally feel straight begins to bend naturally. This bending is not sudden. It increases gradually as gravity becomes stronger, guiding objects along predictable trajectories. One important region around a black hole is called the innermost stable orbit. This is the closest distance at which matter can circle the black hole without falling inward. Beyond this point, no stable orbit exists. Matter continues spiraling closer, not because it is pulled violently, but because no balanced path remains. This transition happens smoothly. Matter does not suddenly lose control. It simply follows the geometry of space as it changes. The boundary between stability and infall is defined by physics rather than force. Rotation plays a major role here. A rotating black hole allows matter to orbit closer before becoming unstable. Faster rotation means tighter, stable paths. This difference affects how accretion disks behave and how much energy they release. Again, the process is orderly and gradual. The region around a rotating black hole includes an area called the ergosphere. Within this region, space itself is dragged along by the black hole's rotation. Objects inside cannot remain still relative to distant space. They move gently with the flow, guided by the motion of space-time. The ergosphere does not trap objects. It simply alters how motion works. Matter and light can still escape from this region as long as they remain outside the event horizon. The transition between these regions is smooth and continuous. These effects show that black holes are not defined by destruction, but by structure. They shape motion rather than break it. They bend space rather than tear it. Everything near them follows clear rules, even when those rules lead to unfamiliar behavior. Black holes also influence how mass is distributed over time. When matter falls in, its mass adds to the black hole, increasing its gravitational reach slightly. This growth is incremental. Each addition is small compared to the black hole's total mass. Over billions of years, growth becomes noticeable, but never sudden. This slow accumulation reflects the general pace of cosmic change. Large structures evolve slowly. Time, not force, drives their development. Black holes fit naturally into this pattern. Some black holes exist in binary systems paired with stars or other black holes. In these systems, motion becomes rhythmic. Objects orbit one another in repeating cycles. Energy is exchanged gradually, often through gentle transfer of matter. In star black hole systems, matter can flow from the star toward the black hole in a steady stream. This flow can continue for long periods without dramatic events. The system remains stable as long as distances remain balanced. Binary black hole systems are even quieter until they begin to merge. For most of their existence, they orbit each other slowly, losing energy at an almost unnoticeable rate. Only in the final moments does motion accelerate briefly, before settling again. These mergers do not disrupt the surrounding universe. Their effects are localized and temporary. Afterward, space returns to calm, carrying only faint ripples that pass through without consequence. Black holes also help us understand limits. They show how dense matter can become without breaking the universe. Even at extreme densities, physical laws remain consistent from the outside. The universe accommodates extremes without instability. This ability to hold extremes within balance is one of the universe's defining traits. Black holes are part of that balance, not exceptions to it. As you listen, these distant systems continue their slow motion. Orbits repeat, space curves gently. Time flows evenly. Nothing demands attention or anticipation. The narration continues at the same pace, steady and unhurried, allowing thoughts to drift and rest, to deepen naturally as the night goes on. Black holes also change how we think about distance. Near one, distances that appear short on a map of space can behave as if they are much longer. Space itself is stretched by gravity, meaning that traveling inward takes more time and effort than it would elsewhere. This stretching is not visible, but it shapes every path near the black hole. Because of this, approaching a black hole is not like falling into a pit. Motion slows gradually as space becomes more curved. Each step inward covers less apparent distance, while requiring more change in position through space-time. This creates the impression of slowing without resistance, guided entirely by geometry. This geometric view helps explain why black holes are so stable. Nothing needs to hold them together. Space itself forms the structure. Matter follows paths determined by curvature, and those paths remain consistent over time. Stability emerges naturally. Black holes also affect how energy is stored and released. When matter moves in strong gravity, energy can be extracted in subtle ways. In rotating black holes, some energy can be taken from the black hole's rotation through interactions in the surrounding region. This process does not weaken the black hole suddenly. It reduces rotation very slowly over immense spans of time. Even this slow loss follows strict limits. A black hole cannot be drained completely. It approaches a stable state where no further extraction is possible. This again shows how extremes are balanced rather than exhausted. The environment around black holes can vary greatly. Some are surrounded by dense gas and dust. Others exist in near-perfect isolation. Their behavior reflects this environment. Where matter is present, gentle activity may occur. Where space is empty, nothing happens at all. Isolated black holes are among the quietest objects in the universe. They emit no light, no sound, and no signal. They drift through space, detectable only by their gravitational influence. Many likely pass unnoticed through galaxies, far from any star. These wandering black holes may have been ejected from their original locations after interactions or mergers. Once free, they travel on long paths through interstellar space. Their journeys take millions of years, guided only by gravity. Despite their motion, these black holes rarely interact with anything. Space is vast, and encounters are uncommon. This reinforces the idea that black holes are not active agents. They respond only when something comes close. Black holes also highlight the difference between appearance and reality. From far away, a black hole is indistinguishable from any other object of the same mass. Its unique properties become relevant only very close by. Most of the time, those properties remain hidden. This hidden nature is why black holes were proposed long before they were observed. They emerged from equations first, appearing as solutions that seemed strange but consistent. Only later did evidence confirm their existence. The process of confirmation was gradual. No single observation proved black holes existed. Instead, many small pieces of evidence accumulated over time. Each observation fit the same pattern, reinforcing the idea quietly and steadily. This slow accumulation of knowledge mirrors the objects themselves. Understanding did not arrive suddenly. It grew patiently, shaped by careful measurement and time. Black holes continue to challenge assumptions without disrupting understanding. They show that intuition based on everyday experience does not always apply, yet deeper consistency remains. They also remind us that the universe does not need to be simple to be calm. Complexity can exist without noise or urgency. The most extreme objects can be the most stable. As you listen, these distant black holes remain unchanged. They do not grow closer, they do not act. They continue shaping space gently, far beyond immediate awareness. The universe moves on at its own pace. Space stretches. Time flows evenly. Motion follows quiet paths. Nothing demands attention. The narration continues in the same way, steady and unhurried, allowing rest to deepen naturally as thoughts soften and drift. Black holes also invite us to think differently about boundaries. The event horizon is often described as a surface, but it is not a physical wall. Nothing marks it visibly. There is no line in space that can be seen or touched. It is simply a region where the paths of light and matter change in a fundamental way. From far away, the event horizon appears still and smooth. It does not ripple or shimmer. It does not react when something crosses it. This calm appearance reflects the stability of the black hole itself. Nothing dramatic happens at the boundary from an external point of view. This quiet boundary separates two regions of space-time. Outside, events can influence the wider universe. Inside, information cannot travel outward. This separation is absolute, yet it does not require force or structure. It arises naturally from how gravity shapes space. Because of this, black holes are sometimes described as simple objects. They can be fully described by a small set of properties: mass, rotation, and charge. Everything else about what falls in becomes inaccessible to the outside world. This simplicity is not emptiness. It is a reflection of how much information is hidden. The idea that information is hidden rather than destroyed is important. It suggests that the universe preserves consistency even in extreme situations. Black holes do not erase the past, they conceal it behind boundaries that cannot be crossed outward. This concealment has led scientists to think deeply about the nature of information itself. Information in physics is not just data. It is a measure of order and structure. If information were lost, it would imply a breakdown of physical laws. Current theories suggest this does not happen. Instead, information may be stored in subtle ways on the surface of the event horizon. This idea is still being explored, but it reinforces the theme that black holes are orderly, not chaotic. Black holes also challenge the idea of a single, universal clock. Near strong gravity, different observers measure time differently. These differences are not contradictions. They are natural outcomes of how time is linked to motion and gravity. This means that descriptions of events near black holes depend on perspective. From far away, processes appear slow. From nearby, they appear normal. Both descriptions are correct within their own frames. The universe allows multiple valid viewpoints without conflict. These differences do not affect daily life. They occur only in extreme environments far beyond Earth. Still, they reveal how flexible time can be when gravity becomes strong. Black holes also influence how we think about beginnings and endings. Matter that crosses the event horizon does not reach an observable endpoint. From the outside, it simply fades away. The process does not conclude in a visible way. It becomes inaccessible rather than finished. This idea applies on cosmic scales as well. Many processes in the universe do not end sharply. They transition into states that are quieter and harder to observe. Black holes exemplify this kind of transition. The universe seems to favor gradual change over sudden resolution. Even when dramatic events occur, they are brief compared to the long periods of calm that follow. Black holes are also reminders that emptiness can be structured. The space around them is not empty in a simple sense. It has shape, direction, and influence. Paths are guided by curvature rather than force. This view of space as something active helps explain many cosmic phenomena. It shows how large-scale structure can exist without rigid frameworks. Space itself provides the framework. As black holes persist, they become part of the long-term structure of the universe. They may outlast stars, planets, and even galaxies. Their quiet presence will remain as space continues to expand and change. In the distant future, when much of the universe grows dark and cold, black holes will still exist. They will continue shaping space locally, even as distances between objects increase. This endurance gives black holes a timeless quality. They do not belong to any particular era. They form, persist, and slowly evolve across immense spans of time. As you listen, these distant objects remain far beyond reach, unaffected by attention. They continue their slow existence, shaped by gravity and time. The universe remains steady. Space curves gently. Time flows evenly. Nothing rushes or demands focus. The narration follows this same rhythm, moving quietly and consistently, allowing rest to deepen as the night continues. Black holes also change how we understand motion itself. In everyday life, motion feels simple and direct. Objects move from one place to another through space. Near a black hole, motion becomes more subtle. Paths are not just influenced by force, but by the shape of space-time itself. Objects follow curves that are natural rather than imposed. This means that falling toward a black hole is not a struggle against gravity. It is a smooth continuation along a path that space provides. There is no sudden pull or acceleration that feels unnatural. Motion unfolds according to geometry, not urgency. Because of this, black holes do not need to consume energy to attract matter. They do not reach outward. Matter moves inward only if it is already on a path that leads there. Most matter in the universe is not on such a path, which is why black holes remain quiet for so long. This geometric view also explains why orbits around black holes can be stable. As long as a path exists that curves around the black hole without crossing the event horizon, motion can repeat indefinitely. Stars, gas, and even light can follow these repeating paths without disruption. When those paths no longer exist, motion changes naturally. Matter transitions from orbiting to falling inward, not because something breaks, but because the available routes through space have changed. The universe adjusts smoothly. Black holes also highlight how direction loses meaning near extreme gravity. Concepts like up and down, inward and outward become less clear. What remains consistent is the flow of time along each object's path. That flow continues without interruption. This is important because it shows that black holes do not trap objects in a moment. Time does not stop. It simply behaves differently depending on perspective. Each object carries its own experience of time forward. From far away, the slowing of time near a black hole appears dramatic. From nearby, it feels ordinary. These differences coexist without contradiction. The universe allows multiple descriptions at once. Black holes also influence how matter organizes itself. Gas clouds near them often flatten into disks. Motion aligns. Chaos reduces. The strong gravity encourages order rather than randomness. Paths become predictable. This ordering effect is seen on many scales. Even in large galaxies, matter tends to settle into rotating structures. Black holes contribute quietly to this tendency by shaping local motion. Despite their influence, black holes do not dominate their surroundings. Their reach is limited. Beyond a certain distance, their effects become indistinguishable from those of other massive objects. The universe remains balanced. Black holes are also excellent examples of how extreme environments can still be governed by simple rules. No new laws are required to describe their behavior from the outside. Gravity, motion, and time interact in consistent ways. This consistency is reassuring. It shows that the universe does not become unpredictable at extremes. It becomes more precise. Black holes also help scientists test ideas about the fabric of reality. By comparing predictions with observation, they refine their understanding of how space and time work together. Each observation adds clarity rather than confusion. These insights do not change the black holes themselves. They remain what they are: quiet, massive, and distant. Knowledge grows around them without altering their nature. As time passes, black holes continue their steady existence. They rotate, drift, and shape space gently. They do not age quickly. They do not rush toward change. The universe around them continues expanding. Distances increase. Motion remains smooth. Time flows evenly. As you listen, there is no need to imagine movement or approach. These objects remain far away, part of a universe that operates calmly and consistently. The narration continues in the same way, steady and unhurried, allowing thoughts to soften and rest to deepen as the night goes on. Black holes also help illustrate how scale changes perception. On human scales, gravity feels weak and constant. On cosmic scales, gravity shapes entire structures. Near a black hole, this shaping becomes more noticeable. Not because gravity becomes aggressive, but because space itself responds more strongly to mass. This change in scale does not introduce new behavior. It reveals existing behavior more clearly. Black holes act as natural magnifiers of gravitational effects, allowing us to observe processes that are otherwise too subtle to notice. One such process is the stretching and compression of space-time. Near a black hole, distances measured by different observers can vary. What appears short from one perspective may be long from another. This is not illusion. It reflects how space adjusts to gravity. These adjustments do not disrupt motion. They guide it. Objects follow the paths space provides. The universe does not require effort to maintain this order. Geometry does the work. Black holes also show how mass and energy are deeply connected. The mass of a black hole represents energy compressed into a small region. This energy curves space, shaping motion and time around it. Nothing extra is needed. No hidden forces act. Because of this, black holes are remarkably simple. Despite the complexity of their formation, they settle into states defined by only a few parameters. This simplicity makes them easier to describe than many less extreme objects. The simplicity of black holes does not reduce their mystery. Instead, it deepens it. How something so simple can hide so much information is one of the most intriguing questions in modern physics. Black holes also influence their surroundings through absence rather than presence. Where light does not escape, darkness remains. This darkness does not spread. It simply marks where observation ends. This boundary between observable and unobservable is a natural feature of the universe. It appears in many forms, not only in black holes. There are always limits to what can be seen, measured, or known. Black holes make those limits clear without creating confusion. They show where understanding transitions into uncertainty without breaking continuity. Over time, black holes may slowly change through subtle processes. Hawking radiation, if fully understood, suggests that black holes emit tiny amounts of energy. This emission is so weak that it has no noticeable effect on current cosmic structures. For now, black holes remain effectively constant. They do not shrink or grow rapidly. They persist, carrying mass forward through time. In the distant future, long after stars have faded, black holes may become some of the last concentrated forms of mass. Even then, they will change slowly, guided by the same principles that govern them now. This endurance reinforces their calm nature. Black holes are not fleeting phenomena. They are long-term features of the universe. As you listen, these distant objects remain unchanged. They do not respond to attention. They do not act or react. They simply exist. The universe continues at a steady pace. Space stretches. Time flows. Motion follows gentle curves. The narration remains unhurried, matching the quiet persistence of these cosmic structures, allowing rest to deepen naturally as the night continues. Black holes also help clarify the relationship between certainty and uncertainty in the universe, in a way few other objects can. From a distance, they are among the most predictable structures known to physics. Their gravitational influence follows precise mathematical descriptions. Their mass can be measured. Their motion through space can be tracked. Given enough information, their external behavior can be forecast far into the future. At the same time, black holes contain regions that remain completely inaccessible to observation. No signal from within the event horizon can reach the outside universe. This means that while the outer behavior of a black hole is well understood, its interior remains hidden. This coexistence of clarity and mystery is not a flaw in nature. It is a feature. The universe often separates what can be known from what cannot, without creating conflict between the two. Black holes demonstrate this separation clearly. They allow the outside world to remain orderly and predictable, while enclosing regions where current knowledge ends. The boundary between these regions is stable, quiet, and well-defined. This balance between the known and the unknown appears throughout nature. Oceans have calm surfaces and unexplored depths. Planets have visible skies and hidden interiors. Black holes express this pattern on the largest possible scale, showing that mystery does not require instability. Black holes also show how extremes can be isolated without spreading outward. The intense curvature of space near the event horizon does not leak into the rest of the universe. It remains confined to a small region. Beyond a certain distance, gravity behaves exactly as it does around any other massive object. This containment is essential for cosmic stability. It allows the universe to host environments of extreme density and curvature without disturbing surrounding regions. Black holes do not tear space apart. They fold it inward gently, keeping the effects localized. Because of this, black holes are not threats to cosmic order. They are part of it. Their presence adds complexity without creating chaos. They demonstrate that the universe can accommodate extremes while remaining calm overall. Another important aspect of black holes is how they preserve motion. Angular momentum, the tendency of objects to keep rotating, plays a central role in their behavior. Matter falling toward a black hole almost never falls straight in. Even a tiny sideways motion becomes important near strong gravity. As a result, matter organizes itself into rotating structures. Disks form naturally. Rings emerge. Motion becomes layered and ordered. These patterns are not imposed. They arise because geometry favors them. The universe prefers smooth motion over abrupt change. These rotating structures can persist for long periods. Accretion disks may remain stable for millions of years, slowly feeding the black hole while releasing energy gradually. Nothing about this process is sudden. It unfolds at a measured pace, guided by conservation laws that never fail. Even when matter finally crosses the event horizon, there is no sudden halt. From its own perspective, motion continues forward in time. There is no sharp transition, no physical boundary encountered. The idea of a dramatic crossing exists only in imagination, not in physical experience. From far away, however, the story looks different. Signals slow, light fades, motion appears to freeze. Both descriptions are correct within their own frames of reference. The universe allows multiple viewpoints without contradiction. This ability to support different perspectives is one of the most profound lessons black holes offer. Reality is not defined by a single observer. It depends on position, motion, and gravity. Black holes make this relativity visible in a way few other objects can. Black holes also deepen the connection between gravity and acceleration. Near the event horizon, the effects of gravity closely resemble those experienced in accelerating frames of reference. This similarity reinforces the idea that gravity is not a force acting through space, but a feature of space itself. Seen this way, black holes are not exotic intrusions. They are natural outcomes of how space responds to mass. When enough mass is concentrated, space curves inward, smoothly, forming a region from which light cannot escape. No additional mechanisms are required. This perspective simplifies many questions. Instead of asking how black holes pull things in, we ask how space is shaped. Instead of imagining destruction, we see geometry guiding motion. Once formed, black holes require no energy to maintain themselves. They do not burn fuel. They do not radiate significantly. They persist without effort. This makes them some of the most stable structures in the universe. This passive stability contrasts strongly with stars. Stars must constantly produce energy to resist collapse. Their lives are active, dynamic, and temporary. Black holes represent a state where balance no longer requires work. This does not make black holes lifeless or empty. Mass remains, energy remains, motion continues. Everything that formed the black hole still exists in a different arrangement. Black holes also act as quiet records of cosmic history. Their mass reflects the amount of matter that has passed through their region. Their location reflects the environment in which they formed. Each black hole carries a story, encoded silently in its properties. That story does not announce itself. It does not glow or signal. It remains hidden unless carefully studied. History becomes something inferred rather than displayed. As the universe expands, black holes remain bound to their local regions. They do not participate in expansion directly. Space stretches between galaxies, but within galaxies, gravity maintains structure. Black holes remain anchored, steady, and unmoved. This separation between cosmic expansion and local stability is one of the most calming features of the universe. Change happens without collapse. Growth occurs without disruption. Black holes will likely persist long after stars fade and galaxies drift apart. In the distant future, they may become some of the last remaining concentrated forms of mass. Even then, their change will be slow, guided by subtle processes that unfold over unimaginable spans of time. This endurance gives black holes a timeless quality. They are not events. They are conditions. They do not rush toward outcomes. They simply remain. As you listen, these distant objects continue their quiet existence, unchanged by attention or awareness. They rotate slowly. They shape space gently. They persist without urgency. The universe remains steady. Space curves softly. Time flows evenly. And the narration continues in the same way, unhurried and consistent, allowing rest to deepen naturally, carried by the same calm principles that govern even the darkest and most mysterious regions of the cosmos. Black holes also reshape how we think about permanence. In a universe where stars burn out, planets drift, and galaxies slowly change shape, black holes remain. They are among the most enduring structures known, persisting long after the processes that created them have ended. This persistence is not dramatic. It is quiet and steady. Once a black hole forms, it enters a state where change becomes extremely slow. Its mass remains nearly constant. Its rotation decreases only gradually. Its position within a galaxy shifts gently over millions of years. Compared to the lifetimes of stars or even civilizations, black holes feel timeless. This sense of permanence comes from simplicity. Black holes shed complexity as they form. The detailed structure of the star that collapsed is no longer visible. Layers, temperature differences, and internal motion disappear behind the event horizon. What remains is a compact object defined by only a few measurable properties. This loss of visible detail does not mean loss of existence. It means that complexity has been hidden rather than destroyed. The universe does not discard what it creates. It rearranges it into forms that are quieter and more stable. Black holes therefore represent a kind of cosmic settling. Where stars are active and changing, black holes are resolved. Where energy once flowed outward, it now remains contained. Motion continues, but without excess. This containment influences how surrounding space behaves. Near a black hole, space becomes smooth and deeply curved. There are no sudden edges or breaks. Everything transitions gradually. Paths bend gently. Time stretches calmly. The universe does not introduce sharp boundaries where continuity would break. This smoothness is essential. It allows black holes to exist without disrupting the larger structure of space-time. Even at the edge of the event horizon, where escape becomes impossible, physical laws remain intact. Nothing tears, nothing snaps. Black holes also deepen our understanding of limits. They show that there are regions where observation ends, not because reality stops, but because information can no longer travel outward. This distinction is subtle but important. The universe continues beyond what can be seen. This idea applies more broadly than black holes alone. At every scale, there are limits to perception. There are depths that cannot be reached, and distances that cannot be crossed. Black holes simply make this principle visible on the largest scale. Yet these limits do not create emptiness. They create quiet. Where observation ends, consistency remains. The universe does not become chaotic beyond knowledge. It continues smoothly, governed by the same underlying structure. Black holes also influence how we think about endings. When something crosses the event horizon, it does not end in a dramatic sense. From the outside, it fades from interaction. It becomes part of a region that no longer communicates outward. The process is gradual and calm. This kind of ending mirrors many natural processes. Rivers flow into oceans. Sounds fade into silence. Light dims into darkness. Black holes follow this pattern on a cosmic scale, turning activity into stillness without violence. In this way, black holes are not symbols of destruction, but of transition. They mark where change becomes slow, where motion becomes contained, where activity becomes background. As time continues, black holes quietly influence their surroundings. They shape the motion of nearby stars. They guide gas clouds. They anchor galactic centers. All of this happens without urgency or noise. Even the most massive black holes do not dominate their galaxies. They coexist with billions of stars, each following its own path. Gravity binds these systems together gently, maintaining balance across vast distances. Over unimaginable spans of time, the universe itself will change. Expansion will carry galaxies farther apart. Stars will become rarer. Energy will spread thinly through space. Through all of this, black holes will remain, steady markers of mass and curvature. Eventually, even black holes may change. If Hawking radiation behaves as predicted, they will very slowly lose energy. This process will take longer than any familiar timescale. For now, it is only a distant possibility, not an active force. This potential fading does not diminish their calm nature. It reinforces it. Change happens, but only at the slowest possible pace. Nothing rushes toward disappearance. Black holes, therefore, embody one of the universe's most consistent themes: stability through patience. They show that even the most extreme conditions can settle into long-lasting balance. As you listen, these distant objects remain far beyond reach, unaffected by awareness. They continue shaping space quietly, carrying mass and time forward without effort. The universe remains calm. Space curves gently. Time flows evenly, and the narration continues in the same way, steady and unhurried, allowing rest to deepen naturally as the night carries on and the cosmos remains quietly at work. Across the universe, there are places where change slows almost to stillness, regions where motion becomes subtle and time seems to stretch. These are not empty places, nor are they chaotic. They are shaped by gravity, acting patiently over immense spans of time. In such regions, mass gathers into stable forms. Once enough mass concentrates, space responds by curving inward. Paths bend naturally, and motion follows routes that feel inevitable rather than forced. This is how black holes settle into the fabric of the universe, not as intrusions, but as natural outcomes. From a distance, nothing about these regions appears unusual. Stars continue moving along predictable orbits. Light travels as expected. Space remains quiet. Only careful measurement reveals that something massive and compact lies at the center, influencing everything nearby without announcing itself. This quiet influence extends far beyond what is immediately visible. Gravity does not end at the event horizon. It reaches outward, shaping the motion of stars and gas across large regions of space. Yet its strength fades smoothly with distance, blending into the broader gravitational field of the galaxy. Because of this gradual fading, most objects remain unaffected. Stability is the default state. Change requires proximity, and proximity is rare. Space offers distance generously, allowing systems to persist without interference. The environment around a black hole often becomes ordered rather than disturbed. Gas clouds flatten into disks. Motion aligns into rotation. Random paths give way to smooth curves. Strong gravity encourages structure, not chaos. These structures evolve slowly. Material circulates, loses energy, and drifts inward over long periods. At no point does the system demand urgency. Everything unfolds according to balance and conservation, guided by geometry rather than force. Rotation plays a subtle but important role. As space itself twists around a rotating mass, nearby motion becomes coordinated. This twisting does not accelerate events. It organizes them. Direction becomes relative, but consistency remains. In these conditions, familiar ideas like center and edge lose some of their meaning. What matters instead is how paths connect through space-time. Objects follow these paths without resistance, as if guided by a quiet current. The notion of falling also changes here. Fallen is not a plunge, but a continuation. An object moves forward in time, along a path that space provides. There is no moment of surrender or loss of control. Motion remains smooth and uninterrupted. From afar, this motion appears slow. Signals take longer to return. Light stretches and fades, yet these effects are gentle. Nothing snaps or breaks. The universe transitions rather than interrupts. These transitions reflect a broader pattern. Across cosmic history, change rarely happens all at once. Stars take millions of years to form. Galaxies evolve over billions. Even the most energetic events occupy only brief moments compared to the calm that surrounds them. Black holes fit into this pattern naturally. They are not constant events. They are long-lived conditions. Once formed, they remain, adjusting only slightly as time passes. Their persistence allows them to act as anchors within galaxies. Stars orbit, gas circulates, motion repeats. Over time, this repetition creates rhythm rather than disruption. Even when two black holes approach one another, their interaction unfolds gradually. Orbits tighten over vast periods. Energy leaks away through faint ripples in space-time. Only at the very end does motion briefly accelerate, before settling again into calm. After such mergers, the resulting object quickly returns to simplicity. Irregular motion fades. Excess energy disperses. Stability reasserts itself. The universe prefers balance, and it restores it efficiently. This tendency toward equilibrium appears everywhere. Disturbances are temporary. Calm endures. Black holes exemplify this principle clearly, holding extreme conditions within stable boundaries. They also remind us that not everything needs to be visible to be real. Much of what shapes the universe cannot be seen directly. Gravity itself is invisible. Space-time curvature has no color or texture, yet these unseen features determine how everything moves. Understanding this allows a different kind of curiosity to emerge, one that does not seek spectacle, but coherence, one that finds meaning in consistency rather than surprise. As you listen, there is no need to imagine approaching anything. These regions remain distant, unaffected by attention. They continue their slow existence, whether observed or not. The universe remains steady. Space curves gently. Time moves forward evenly, and the narration continues alongside it, unhurried and calm, offering a quiet companion as rest deepens and the night continues without urgency. Far from any sense of urgency, the universe allows even its most extreme structures to settle into routine. Motion becomes repetitive. Paths repeat. Patterns stabilize. Around black holes, this rhythm is especially clear because gravity shapes everything gently but firmly. In many regions, stars trace long, slow arcs around an unseen center. These motions can be measured across decades, revealing orbits that remain steady over enormous spans of time. Nothing about these movements suggests danger or collapse. They are calm expressions of balance. The space surrounding a massive object does not resist motion, it guides it. This guidance is smooth, almost effortless. Objects follow the curves that space provides, just as water follows the shape of a riverbed. No force needs to be applied once the path exists. This is why black holes do not create constant disruption. Their influence is structural rather than aggressive. They define geometry, and geometry does the rest. Over time, matter near these regions organizes itself naturally. Gas clouds thin out, particles align their motion. What begins as diffuse and uneven becomes layered and coherent. Strong gravity reduces randomness, turning disorder into pattern. These patterns can persist for millions of years. Accretion disks slowly circulate. Jets, when present, remain narrow and stable, pointing in fixed directions for vast distances. Even these dramatic-looking features are governed by steady rules and long-term balance. Not every black hole produces visible structures. Many exist in near-total isolation, surrounded by empty space. These objects may never interact with another star or cloud. They remain undetected, passing silently through galactic neighborhoods. Such isolation highlights how sparse the universe truly is. Even in regions filled with stars, the average distance between objects is enormous. Encounters are rare. Stability dominates. Because of this, black holes spend most of their existence inactive. They are not constantly growing. They are not constantly feeding. They wait, not deliberately, but naturally, responding only when something passes close enough. This responsiveness without intention is important. Black holes do not act. They react. They do not initiate change. They accommodate it. This distinction removes much of the fear often associated with them. Without agency or appetite, they are simply regions of curved space, following the same laws as everything else. Their effect on time is equally passive. Time slows near strong gravity, but it does so smoothly. There is no sudden shift, no moment where time stops or breaks. The flow remains continuous. Different observers experience this flow differently, depending on their position and motion. Yet these experiences fit together consistently. The universe does not contradict itself. It allows multiple perspectives to coexist. This flexibility extends beyond black holes. It is a general feature of reality. Space and time adjust to mass and motion everywhere. not only in extreme environments. Black holes simply make this adjustment easier to notice. They also provide a natural laboratory for testing ideas about the universe. By observing how matter and light behave near them, scientists refine their understanding of gravity and space-time. Each observation adds precision rather than uncertainty. Still, many questions remain open. The interior structure, the ultimate fate of infalling matter, and the deep connection between gravity and quantum physics are not fully understood. These unknowns do not disrupt the calm picture. They sit quietly at the edges of knowledge. The presence of unanswered questions does not imply instability. It implies depth. The universe does not reveal everything at once. It unfolds gradually, allowing understanding to grow over time. As the universe ages, black holes continue to serve as long-term features. They persist while other structures change. Their influence remains local, contained, and steady, even as galaxies drift farther apart. Due to cosmic expansion, black holes remain bound within their systems. They do not pull galaxies together. They do not resist expansion. They coexist with it. This coexistence between local gravity and global expansion is one of the universe's most balanced arrangements. Stability and change operate simultaneously, each in its own domain. As you listen, there is nothing here that requires focus or interpretation. These processes continue without observation. They are steady, whether noticed or not. The narration mirrors this steadiness. It moves forward quietly, without urgency, allowing rest to deepen naturally as the night continues, and the universe remains calmly in motion. There is a quiet patience built into the structure of the universe, one that becomes more noticeable the longer you observe it. Nothing insists on immediate change. Even in regions where gravity reaches its most extreme forms, motion unfolds slowly, guided by balance rather than force. Near black holes, this patience is not hidden. It becomes part of the environment itself. Over long spans of time, nearby stars adjust their paths almost imperceptibly. Small changes in mass or position ripple outward, but these ripples travel slowly. Orbits do not collapse or destabilize suddenly. Instead, they shift gently, settling into new patterns that remain stable for millions of years. This process is continuous and calm. What stands out is how little effort is required to maintain this order. Once paths are established, they persist naturally. Space itself carries the instructions for motion. Objects do not need to be pushed or held in place. Geometry replaces force, and balance replaces tension. This is why black holes do not need to hold on to anything around them. Gravity does not grip or pull in the way it is often imagined. It curves space, and objects follow those curves because they are the easiest path available. Nothing is compelled. Everything simply continues. Even when matter drifts inward, the process remains slow and measured. Gas spirals gently, completing countless rotations before moving noticeably closer. Energy is released gradually in small amounts, spread out over long periods. Heat builds slowly. Light is emitted softly. There is no sudden collapse, no moment of urgency. The presence of a boundary still matters. The event horizon marks the region beyond which paths no longer lead outward. But this boundary is not a wall. It is not abrupt. It represents a smooth transition in how space and time behave. There is no signal, no visible marker, no change in texture or structure. Because of this, reality remains continuous. Nothing breaks at the edge of the observable. Space does not tear. Time does not stop. Motion continues forward without interruption. The universe does not introduce sharp endings where continuity would fail. This continuity is one of the most reassuring aspects of cosmic structure. It shows that even when knowledge has limits, order remains intact. The unknown does not imply disorder. It simply marks where observation can no longer follow. Black holes also provide insight into how the universe handles memory. Information about what falls inward does not vanish in a physical sense. It becomes inaccessible, hidden behind boundaries that cannot be crossed outward. This is not erasure, it is concealment. The distinction matters. A universe that preserves information, even when it cannot be retrieved, is one that maintains consistency. Laws do not break at extremes. They continue operating quietly, even where observation ends. This idea fits a broader pattern. Across nature, processes rarely destroy completely. They transform. Matter changes state. Energy spreads. Motion reorganizes. Black holes represent an extreme version of this transformation, where activity becomes contained rather than eliminated. Over cosmic history, these regions accumulate matter slowly. Their mass reflects countless past events. Stars that exhausted their fuel, gas clouds that drifted inward, mergers that reshaped entire systems. Each black hole carries a silent record of these events, encoded in its mass and rotation. Yet this record does not announce itself. It does not glow or signal. It remains background rather than foreground. The universe does not require history to be displayed in order to persist. As time continues, black holes remain anchored within their local environments. They do not expand with the universe itself. While space stretches between galaxies, gravity keeps local systems bound. Stars continue orbiting. Structures remain intact. This separation between local stability and global expansion is one of the universe's most balanced arrangements. Change and persistence coexist without conflict. Growth happens without collapse. Stability survives within motion. In a distant future, long after many stars have faded and galaxies have grown dim, black holes will still exist. They will not dominate the universe. They will simply remain quiet concentrations of mass in an increasingly sparse cosmos. Even then, change will not stop. If current theories are correct, these objects will slowly release energy through subtle processes. This release will take place over timescales so vast they defy comparison. Nothing will rush toward disappearance. This slow fading reinforces a consistent theme. The universe avoids sharp conclusions. It prefers gradual transitions. Things do not end suddenly. They thin, dim, and quiet over time. Black holes embody this preference clearly. They are not final points. They are long pauses in cosmic evolution, states where motion continues without outward display, where activity becomes background. As you listen, these distant regions remain far beyond reach, unaffected by awareness. They do not respond. They do not change course. They continue shaping space softly, governed by the same steady rules that guide everything else. The universe remains calm. Space curves gently. Time flows evenly without urgency or demand. And the narration continues alongside it, unhurried and consistent, offering a quiet presence as rest deepens, and the night carries on, steady and uninterrupted. Beyond what can be observed directly, the universe continues to operate with remarkable consistency. Even in regions shaped by extreme gravity, nothing behaves randomly. Motion follows rules that remain unchanged across time and distance. Near black holes, these rules become clearer, not because they are different, but because they are expressed more fully. In these environments, the relationship between cause and effect stretches over long periods. Small changes take time to matter. A slight shift in mass distribution may take millions of years to alter surrounding orbits. Nothing responds instantly. The universe allows adjustments to unfold gradually, preserving stability. This slow responsiveness is essential. It prevents chain reactions. It ensures that local changes remain local. Even when black holes gain mass through infalling matter or mergers, the effects spread outward gently, giving surrounding systems time to adapt. Adaptation is a quiet process in space. Orbits adjust. Gas redistributes. Motion settles into new patterns without disruption. The universe does not correct itself forcefully. It relaxes into balance. These balances depend heavily on symmetry. Gravity acts the same in all directions. Space curves evenly. Time flows smoothly along every path. This symmetry is why even extreme regions remain coherent rather than chaotic. Near black holes, symmetry is preserved in subtle ways. Accretion disks remain thin and flat. Jets, when present, emerge in opposite directions. Motion aligns into repeating structures. Nothing breaks the underlying order. This order does not require design or intention. It emerges naturally from the laws that govern mass and motion. Black holes do not organize their surroundings deliberately. Geometry does the work on its own. The quiet role of geometry is easy to overlook. In daily life, forces feel active and intentional. In the universe, structure often comes from passive relationships. Space provides paths. Objects follow them. Balance emerges without effort. Because of this, black holes do not dominate their surroundings. They influence without control. They shape without directing. Their presence adds curvature, not command. This distinction is important when considering the future of the universe. As expansion continues, large-scale structure will change. Galaxies will drift farther apart. Interactions will become rarer. Yet within bound systems, stability will remain. Black holes will continue anchoring these systems quietly. Stars may fade, gas may thin, but the underlying gravitational structure will persist. Change will slow rather than accelerate. In this future, the universe will not end with a sudden event. It will enter a long period of calm thinning. Energy will spread evenly. Motion will become simpler. Complexity will give way to uniformity. Black holes fit naturally into this outcome. They represent concentrated structure in an increasingly diffuse universe. Their presence will mark regions where mass remains gathered, even as everything else spreads outward. Eventually, even these concentrations may change. If black holes slowly release energy over vast timescales, their mass will diminish. But this process will be gradual beyond comprehension. Nothing will rush toward emptiness. This gradualism reflects the universe's overall character. Nothing is wasted. Nothing is erased abruptly. Everything transitions slowly, preserving continuity. These transitions do not require awareness. They do not depend on observation. They occur whether noticed or not. The universe does not wait for attention. As you listen, these processes continue far beyond reach. Space curves gently. Time flows evenly. Motion remains smooth. There is no climax approaching, no conclusion forming, just steady continuation. The narration follows the same principle. It does not build toward resolution. It remains even and unobtrusive, allowing thoughts to drift without attachment. Rest does not need to be achieved. It arrives naturally when effort fades. The universe demonstrates this constantly, settling into balance whenever disturbance ends. And so as the night continues, these distant structures remain unchanged, quietly shaping space, while awareness softens and the steady rhythm of the cosmos carries everything forward without urgency. Far into the future, when the universe has had time to soften its contrasts, regions shaped by strong gravity will still exist as quiet anchors in an increasingly diffuse cosmos. While stars burn out and galaxies drift farther apart, these regions remain, holding their structure through patience rather than force. Time behaves differently when change slows. In environments dominated by stability, moments lose their sharpness. There are no sudden transitions to mark progress. Instead, evolution becomes a matter of subtle adjustment, unfolding across spans so long they resist ordinary comparison. Black holes belong naturally to this regime of time, where persistence outweighs activity. In such places, gravity no longer acts as something that competes with other processes. It becomes the background condition. Motion, energy, and structure all adapt to it rather than resist it. Objects move because space allows them to, not because they are compelled. This shift in perspective is important. It reframes gravity not as an influence acting on matter, but as the environment in which matter exists. Near massive objects, space itself becomes the medium through which everything moves. The universe does not push, it provides paths. Those paths are smooth, continuous, and deeply stable. Once established, they resist disruption. Orbits repeat, rotations persist. Even small disturbances are absorbed gradually, spreading their effects thinly over time and distance. This absorption prevents extremes from propagating outward. Even when massive events occur, mergers, infall, or rapid rotation, the resulting changes remain contained. Energy disperses, motion settles. The surrounding universe continues almost unchanged. Such containment is not accidental. It is a consequence of symmetry and conservation. Energy cannot appear or disappear suddenly. Momentum must be preserved. Geometry must remain continuous. These constraints work together to ensure calm outcomes, even from dramatic beginnings. Because of this, black holes do not destabilize their environments. They regulate them. Their presence sets boundaries within which motion must conform, encouraging order rather than disorder. Random paths become aligned. Diffuse matter organizes into layered structures. Over time, this organization becomes increasingly refined. Loose gas clouds thin and flatten. Motion becomes more predictable. The system simplifies itself naturally, reducing complexity without external intervention. This tendency towards simplification is widespread across the universe. Early cosmic history was marked by turbulence and rapid change. As time progressed, structure emerged and stabilized. The universe matured, trading intensity for coherence. Black holes are part of that maturation. They represent endpoints where collapse has resolved into balance. Where stars required constant energy to maintain form, these regions require none. They persist without effort. This effortlessness is not emptiness. It is efficiency. Once space has curved into its final shape, nothing more is required to keep it that way. The universe settles and moves on. The idea that something so extreme can also be so calm challenges everyday intuition. Yet this contrast appears repeatedly in nature. Mountains appear solid yet move slowly. Oceans seem restless, yet obey stable patterns. On cosmic scales, the same principle holds. Even the most massive objects do not hurry. Their influence unfolds gently. Their presence shapes outcomes without drama. As cosmic expansion continues, these stable regions become more isolated. Distances grow, interactions become rare. The universe grows quieter, not because activity ceases, but because separation increases. In this quieting universe, black holes become markers of where mass remains gathered. They will not glow or signal. They will simply exist, embedded in local pockets of structure amid vast emptiness. Around them, time will continue flowing, though there may be little to mark its passage. Few new stars will form. Motion will repeat without variation. Change will slow to a near standstill. This future is not an ending. It is a continuation under different conditions. The universe does not conclude. It thins, stretches, and settles. Even then, nothing breaks. Physical laws remain intact. Geometry persists. Motion continues along available paths. If black holes eventually lose mass through extremely slow processes, this too will happen without urgency. Energy will leak away gradually, blending into the background. No event will announce the change. No boundary will collapse. The universe will not notice the difference all at once. It will adjust quietly, as it always does. This capacity for quiet adjustment is one of the universe's most defining traits. It allows complexity to arise and fade without instability. It ensures continuity across unimaginable spans of time. As you listen, these distant futures require no attention. They are not approaching. They are simply possible outcomes unfolding far beyond experience. The present remains calm. Space around you is steady. Time moves forward evenly. The narration follows the same path. It does not build toward a conclusion. It does not demand resolution. It continues gently, offering a steady presence rather than direction. Rest does not need to be reached deliberately. It arrives naturally when effort releases, just as balance emerges naturally when motion settles. And so the universe continues, quiet, patient, and consistent, while awareness softens, thoughts slow, and the night carries everything forward without urgency or demand. As the universe continues to age, it gradually shifts into a state where stillness becomes more common than activity. Motion does not disappear, but it settles into repetition. Large changes become rare. Long periods of balance stretch outward, uninterrupted. In this quieter phase of cosmic history, gravity remains one of the few forces still shaping structure, and its influence is felt most clearly where mass has gathered and remained. In these regions, space no longer feels like an empty background. It behaves more like a gentle framework, one that quietly guides motion without resistance. Paths exist before anything travels along them. Objects move because the structure of space allows movement, not because something pushes or pulls with urgency. This way of understanding influence changes how the universe is perceived. Nothing reaches outward with intent. Nothing draws objects inward through desire or action. Instead, everything responds locally to the shape of space around it. The universe operates through accommodation rather than command. Over immense spans of time, this accommodation produces stability that feels almost timeless. Orbits repeat with minimal variation. Rotations slow only slightly. Patterns established millions or billions of years earlier remain intact. The universe remembers its structure, even as it grows larger and quieter. This memory is not stored in records, signals, or visible traces. It is stored in geometry. The shape of space preserves information about mass, motion, and history. Even when visible matter fades or disperses, that shape remains, guiding what little motion continues. Because of this, the past never fully disappears. It becomes embedded in structure rather than display. Black holes exemplify this embedding clearly. They carry the imprint of countless earlier events without revealing them openly. Their presence is quiet, but their influence reflects deep history. Their mass reflects accumulation. Their position reflects environment. Their rotation reflects past motion. Each of these properties encodes events that unfolded long ago. None of this information needs to be visible for it to remain real. In the absence of frequent interaction, the universe becomes easier to predict. Fewer events interrupt established patterns. Motion settles into repetition. Change stretches out across longer and longer timescales. Where complexity once dominated, simplicity begins to prevail. This does not make the universe empty. It makes it calm. Activity and complexity are phases, not permanent states. Stability is what remains when those phases pass. The universe does not resist this transition. It allows it. In this calmer universe, extremes still exist, but they are contained. Regions of strong gravity remain localized. Their effects fade smoothly with distance. Nothing spreads uncontrollably. Boundaries remain clear and stable. This containment ensures coherence. Even as matter becomes sparse and interactions become rare, structure survives. Systems do not unravel. They persist quietly within their local boundaries, supported by gravity and geometry. Time itself continues without urgency. Without frequent events to mark its passage, time feels open rather than segmented. There are no milestones to approach, no moments demanding attention. Time simply flows. This open quality of time is reflected in how cosmic processes unfold. Even the slowest changes do not aim toward a final moment. They move forward indefinitely, guided by consistency rather than purpose. The universe does not hurry toward an ending. It does not seek completion. It does not move toward resolution. It simply follows its structure wherever that structure leads, allowing outcomes to emerge naturally. In this sense, black holes are not endpoints. They are long-lived states within an ongoing process. They represent regions where motion has become contained, where change has slowed, where balance has been reached without effort. Eventually, if conditions allow, even these states may soften. Energy may spread further. Structure may become simpler still. But these transitions will unfold so slowly that they barely resemble change at all. Nothing about this future is abrupt. Nothing collapses. Nothing stops. The universe does not break or conclude. It thins, stretches, and quiets, carrying everything forward gently. Even processes that involve loss, such as the slow release of energy from extremely stable structures, occur without drama. Energy does not vanish. It disperses. Contrast fades. Differences smooth out. This smoothing is one of the universe's defining tendencies. Sharp edges soften. Extremes relax. Over time, everything moves toward balance rather than away from it. As you listen, none of these distant processes require effort or attention. They are far beyond reach and unaffected by awareness. They continue whether noticed or not. The present moment remains steady. Space around you is calm. Time moves evenly without pressure. The narration follows the same rhythm. It does not build toward a conclusion. It does not demand understanding. It continues gently, offering a steady presence rather than direction. Rest does not need to be achieved. It arrives naturally when effort releases, just as balance emerges naturally when motion settles. And so the universe continues, quiet, patient, and consistent, while awareness softens, thoughts slow, and the night carries everything forward, unbroken and unhurried. Slowly, the universe settles into patterns that repeat without effort. What once felt dynamic becomes steady. Motion remains, but it no longer surprises. Paths are well established, and objects follow them without deviation. This is not stagnation, it is maturity. In this mature universe, gravity continues its quiet work. It does not seek to gather everything together, nor does it allow everything to drift apart unchecked. It maintains balance locally, holding structures together even as the larger cosmos expands. This balance is subtle and deeply stable. Within these stable regions, mass no longer rushes toward dramatic outcomes. Stars that still exist move predictably. Gas that remains circulates slowly. Energy spreads gently, avoiding sharp concentrations. The universe prefers equilibrium when given enough time. This preference becomes especially visible near regions of extreme curvature. There, motion is guided so precisely that even complex systems simplify themselves over time. Irregular paths smooth out. Excess energy dissipates. What remains is order without effort. One of the most striking aspects of this order is how little intervention it requires. Nothing needs to manage it. There is no correction mechanism operating in the background. The structure of space itself ensures that motion remains coherent. This coherence is why black holes can exist without destabilizing their surroundings. Their presence does not introduce chaos. It introduces definition. Space curves, paths adjust, and systems settle into configurations that can last for immense spans of time. The universe, in this sense, behaves less like a machine and more like a landscape. Objects move through it, shaped by contours that were formed long before they arrived. Once those contours exist, motion becomes natural and predictable. These contours are not rigid. They respond slowly to changes in mass and motion. Yet this responsiveness is gentle. Adjustments ripple outward gradually, giving surrounding systems time to adapt. Sudden shifts are avoided. Because of this, the universe does not experience cascading failures. A change in one region does not trigger collapse elsewhere. Effects remain local. Stability dominates. Over time, this locality becomes more pronounced. As distances grow and interactions become rarer, each region evolves largely on its own. The universe becomes a collection of quiet islands, of structure separated by vast calm. In such an environment, the concept of eventfulness fades. There are fewer moments that stand out. Time becomes less punctuated by change and more defined by continuity. The universe does not mark its progress loudly. This does not mean nothing happens. It means that what happens unfolds slowly enough to blend into the background. Change becomes texture rather than event. Black holes fit seamlessly into this texture. They do not disrupt the rhythm, they reinforce it. Their stability adds weight to the surrounding calm, anchoring local systems without drawing attention. Their influence remains precise and limited. Beyond a certain distance, their presence becomes indistinguishable from that of any other massive object. The universe does not exaggerate extremes. This moderation is one of its defining characteristics. Even at its most intense, reality remains controlled. Boundaries are respected. Transitions are smooth. The passage of time reflects this moderation. Without sudden changes to track, time feels continuous rather than segmented. There are no sharp before and after moments, just gradual evolution. This quality of time is difficult to imagine from a human perspective, where change often feels immediate. On cosmic scales, immediacy disappears. Patience becomes the dominant mode. The universe does not measure itself against deadlines. It does not seek outcomes. It simply follows its structure forward, allowing each moment to arise from the last. In this unfolding, nothing is wasted. Energy disperses. Matter rearranges. Motion continues along available paths. Even when structures simplify, nothing truly ends. Black holes, long-lived and quiet, embody this principle. They are reminders that persistence does not require activity. Stability does not require maintenance. Some states, once reached, simply endure. As you listen, these distant processes remain far removed from experience. They do not approach or recede. They continue independently of attention. The space around you remains steady. Time continues evenly. Nothing presses for resolution. The narration follows this same rhythm, slow, even, and unobtrusive, allowing awareness to soften, thoughts to slow, and rest to deepen naturally, as the universe continues quietly, without urgency or demand. Eventually, the universe reaches a point where nothing feels unfinished, not because everything has been resolved, but because nothing is in a hurry to become something else. Motion continues, yet it does so gently. Structures remain, yet they no longer compete for change. The cosmos settles into a state where balance outweighs transformation. In this stage of cosmic time, gravity continues its quiet work. It does not gather everything together, nor does it allow everything to drift away without limit. Instead, it maintains local coherence. Where mass remains, structure remains. Where space stretches, separation increases slowly and evenly. Within these remaining pockets of structure, motion becomes repetitive. Orbits repeat. Rotations persist. Paths curve in familiar ways. There is little novelty, but there is great stability. The universe does not seek variety for its own sake. It allows what already exists to continue. Regions shaped by extreme gravity remain among the most stable of all. They do not change quickly. They do not decay in any noticeable way. Their presence is quiet but enduring, anchoring local systems as everything else grows more diffuse. What once seemed mysterious or threatening becomes simply another feature of the cosmic landscape. Black holes are no longer events to be explained, but conditions to be accepted. They represent places where motion has settled, where mass has gathered, where time flows without interruption. The idea of endings becomes less meaningful here. Stars fade rather than stop. Galaxies thin rather than collapse. Energy disperses rather than disappears. Nothing concludes sharply. Everything transitions. This gradual fading reflects a deeper principle. The universe does not favor finality. It favors continuity. Even when structures simplify, they do so without breaking the flow of time or space. In this sense, black holes are not symbols of destruction, but of persistence. They show how extremes can resolve into calm states that last far longer than the active phases that preceded them. As expansion continues, distances grow larger. Interaction becomes rare. Yet within each remaining system, gravity holds quietly, ensuring that local order survives even as the larger universe stretches. Time itself becomes less marked by events. Without frequent change, time feels open and unstructured. There are no milestones approaching, no outcomes waiting to arrive. Time simply passes. This open flow of time is not empty, it is peaceful. It allows everything that remains to exist without pressure. Nothing needs to happen next. Eventually, if the universe continues long enough, even the most stable structures may begin to soften. Energy may spread further. Contrast may fade, but this process will unfold so slowly that it barely resembles change at all. Nothing collapses, nothing ends abruptly. The universe does not reach a final moment. It continues in quieter and quieter forms, always guided by the same simple rules. Through all of this, space remains smooth, time remains continuous, motion remains possible. Reality does not fracture at its edges. Black holes, silent and patient, remain part of this long story. They do not dominate it, they do not conclude it. They simply persist, shaping space gently, long after attention has moved elsewhere. As you listen now, none of this requires effort. These distant futures are not approaching. They are possibilities unfolding far beyond experience. The present remains calm. Your surroundings are steady. Time continues at its normal pace. There is nothing here to solve or remember. The universe does not ask to be understood in order to continue. And so, as the narration slows, it follows the same principle as everything else. It does not stop suddenly. It fades naturally, allowing silence to take over without interruption. You can let the words drift away now. There is nothing more to follow. Everything continues quietly on its own. The universe remains calm. Time keeps moving, and rest can come naturally, without effort, as the night carries on.